Now, let's remember this, I told you we would understand this precession here. You remember the omega vector is the red vector. It always stays the same length, never gets longer or shorter, but it is changing direction. And so that means we have an alpha. And that alpha has to be perpendicular to the omega. Now I want you to take a picture of this system right now. You didn't. Come on, people, work with me. Take a picture of it right now. People, I'm talking to you. Take a picture of it right now. I'll do it. Okay? I'll just freeze time. There, I took the picture. I took the picture right when I was holding this and the alpha vector was moving away from me. Good enough? Everyone got the picture? Okay. Let's see what's causing that alpha. Okay, again, the alpha has to be perpendicular to the omega. So, if the net torque is causing the alpha, and the alpha at this moment we took the picture is pointing away from you, what direction is the net torque? Away from you. Let's show that. Now, here's something new. When we were worried about linear motion, we did not care where the forces were applied. We drew a free body diagram by making any object, no matter how complicated it was, a dot. Because all we cared about was how much force we had to the right, how much force we had to the left, how much force we had up or down. We didn't care where those forces were applied. And that dot represented the center of mass of the object. But when we deal with torque, we very much care about where the forces are applied. So we draw what's called an extended free body diagram. And we draw the object as it appears. And we put on that object the forces where they are applied. Now, in this case, our omega vector is the red arrow pointing towards the open door. The blue vector is the alpha vector pointing away from you. Oops, it's sagging. Okay. Now, if I look at the forces, I have the tension in the rope, and I have the weight force. Now, I applied the weight force here at the center of gravity. And remember, as long as we're close to the surface of the Earth, the center of gravity is the same place as the center of mass. Now, because this wheel is weighted down with lead, all the mass is pretty much here. It's not to the left of there or to the right of there, it's pretty much here. And so I can draw that weight vector as acting right here at the center of the wheel. Now, in order to look for torque, I always have to look for torque about some pivot point. In this case, as I was holding this, it was precessing, it was rotating about this point right here where the rope attaches to the bar. And so that's going to be my pivot right there. Now, let's take these forces one at a time. And we need to talk about what torque do I get from this force. Is it out of the page, into the page, or zero? That one right there. Why is it zero? Oh, not zero? Look at the lever arm. If I extend the line of action goes right through the pivot. There is no lever arm. This is like going up to a door and trying to open it by pushing at the hinge. That doesn't cause rotation. Not about that point. So let's look at so that gives me zero torque. Let's look at the torque due to this weight. I started the pivot. I reach out to the force. I turn my wrist so that I can wave in the direction of the force. My thumb is in the direction of the torque. Now, if I take a zero torque and I add it to a torque into the page, I get a net or total torque into the page, which is causing that alpha. Okay? Check that your neighbor's on the bus.